is Angelica Laine-Escano, and I am going to talk about Z-enol P-tosylate derived from methyl acetoacetate, a useful cross-coupling partner for the synthesis of methyl Z3-phenyl 2-butanoate. The authors are Yuichiro Ashida, Hidefumi Nakatsuji, Yutanabe, Yuji Suzuki. So first, we are going to talk about the scale and optimization. So for these reactions, some of the reagents are expensive. So here they are using still generis reagent and SNOTF2, and TF2O is also expensive than TSCl. So that is a major drawback because TF2O is 15 to 30 times more expensive than TSCl. Also, in addition, TF2O is highly toxic and hazardous with a low boiling point, and it reacts violently with water. Also, reagent 4 that was used in this reaction is not commercially available, which is 1-naphthoxy 2-PCH2CO2-ET. Also, it is corrosive and irritant. It's the same thing as trifluoromethane sulfonic anhydride, which is the TF2O. It is also corrosive. It causes burns. Also, inhalation of this reagent may cause corrosive injuries to upper respiratory tract and lungs. Now we are going to talk about the apparatuses that's used in this reaction. So this reaction comes with part A and part B. With part A, mainly the apparatuses are like the same. The difference is just the volumes of like the 3-necked round bottom flask. So for part A, we are using 500 ml of 3-neck round bottom flask. In part B, we are using 300 ml 3-neck round bottom flask. Also in part A, we have a CaCl2 drying tube, glass stopper, thermometer, Teflon coated magnetic steering bar, glass funnel, ice cooling bath, 50 ml separatory funnel, rotary evaporator, 10 and 100 and 200 ml round bottom flask oil bath. For part B, we have a nitrogen stopcock inlet, a topper, a thermometer, Teflon coated magnetic steering bar, water bath, paper funnel, 300 ml separatory funnel, and a vacuum pump. Okay, so the reagents that or material used in this reaction, we have part A, which is methyl 3-oxobutanoate. We have lithium chloride, TMEDA, ethyl chloride, TSCl, water, ETOAC, 1 mole of HCl, brine, 2-propanol. In part B, we are also using nitrogen, 2-propanol, water, Z-enol tosylate, K2CO3, triphenylphosphine, PTOAC, ETOAC, 1 mole of NaOH, and brine. So for the procedures, since it's part A, part B, for the step A, we are going to form Z3-p-toluene sulfonyloxy butanoate, which is we're gonna call Z1 in this reaction. So first, there's 500 ml of 3-necked round bottom flask that is attached to a CaCl2 drying tube, which is capped with a glass stopper and fed with a thermometer and a Teflon coated magnetic steering bar. With all that stuff, we're gonna add 17.41 grams of methyl 3-oxobutanoate. After that, we're gonna add 7.63 grams of lithium chloride. So that was added in the mixture by portion via glass funnel, and then 26.8 ml of TMEDA EDA that was added like dropwise over 2 minutes to the suspension. And after adding all the materials to the suspension, we're gonna do like ice cooling bath. After the ice cooling, there's a 34.31 grams of TSCL that is added in 3 portions over 15 minutes. So for each addition, the inner temperature was maintained below 10 degrees Celsius. And after that addition of TSCL, the suspension then becomes a well-dispersed white slurry after 10 minutes of addition of TSCL. And then the suspension was stirred for an hour at roughly about 5 degrees Celsius. After an hour, 75 ml of water was added to the solution and the temperature was maintained below 15 degrees Celsius until the solution turned into biphasic solution. The solution was then transferred into a 500 ml separatory funnel. The flask was rinsed twice with ETOAC. So it's kind of like with 20 ml, 10 ml each, which is then added to the separatory funnel. The organic phase is separated and the aqueous phase is re-extracted with ETOC with like 50 ml. And then the combined organic phases were washed with aqueous 75 ml, 1 mole HCl, and 75 ml brine. And it was dried over 75 grams of Na2SO4. It was then filtered, concentrated under reduced pressure using a rotary evaporator to remove the ETOC completely. The slight orange-colored oil solidifies after a few minutes. Crude solid in a 100 ml round bottom flask is crushed into a particle which is then transferred into a 200 ml round bottom flask with 40 ml of 2-propanol. The solid completely dissolved with heated by an oil bath at 50 degrees Celsius. The solution is cooled and resulting solid is collected using a glass funnel and washed twice with 2-propanol to yield a 29.78 to 31.21 grams. So it has like 74% yield of the desired product as white prism. So after the step A, we have step B, which is pretty much the same steps. It's just that the round bottom flask is equipped with nitrogen, stopcock inlet, capped with a topper, equipped with thermometer, and the Teflon magnetic steering bar. So it's kind of like the same setup as a step A. It's just like the flask is flushed with nitrogen, and it was kept under a continuous nitrogen flow. It was charged with 75 ml of 2-propanol and 25 ml of water. The stirred suspension was immersed in a temperature-controlled water bath with 13.52 grams of Z-enol tosylate and 7.26 grams of K2CO3. Those two were added in portion via a paper funnel. The reaction was warmed to 30 to 35 degrees Celsius, and that was the internal temperature. 262 milligrams of triphenylphosphine and 112 milligrams of PDOAC2 were added by portion as well, and the internal temperature was maintained below 40 degrees Celsius. After the addition is completed, the reaction was stirred for an hour. It's the same thing as the part B. The reaction was then cooled down and rinsed with water and washed with like 100 ml of ETOAC. Filtrates is transferred into a 300 ml separatory funnel. The organic phase is separated and the aqueous phase is extracted with 50 ml ETOAC. The organic phases were combined and washed with 50 ml aqueous 1 molar NaOH and 50 ml brine, dried over Na2SO4, filtered and concentrated under reduced pressure using a vacuum pump, gives the desired product of Z2, which is the methyl Z3-phenyl 2-butanoate, and it was collected for like 5.10 to 6.94 grams, which has a 58 to 80% yield. So in this one, the appearance, this one, so like on the farthest, on the middle, right here, that is the addition of p-toluene sulfonyl chloride. The appearance of reaction mixture after addition of reagent was right after the middle, like in this like upper right corner. The biphasic solution was the lower right corner of the slide. Solidified product was the second to the last product, which is below the middle picture, and then the recrystallized product is on the upper left corner of the slide. So this is the reaction workup. So there is two representative methods utilizing the Horner-Wadsworth-Emmons reaction. So for this one, and also we have the method utilizing iron catalyzed cross coupling of enol triflate Z5. So there's a group that pioneered in the iron catalyzed cross coupling of Grignard reagents with an enol triflate of methyl or ethyl acetoate, which is the Z5 in this scheme. So Z5 is synthesized using triflic anhydride, it's TF2O, and NaH, which is from method A. This is a superb method, is the most pertinent to the strategy of the people that worked in this reaction. But the one significant disadvantage is that TF2O is approximately 15 to 30 times more expensive than TSCl. Also, TF2O is highly toxic and hazardous with a low boiling point and a violent reaction with water. So enol triflate Z5 is an oil, but its stability to distillation purification is unknown, so it's purified using only flash column chromatography. And France's group, which is another group that worked in this reaction, developed a practical preparative method for Z5, which is the method B that was described earlier, which also requires flash column chromatographic purification. And this iron cross coupling requires about like 1.8 equivalents of PHMGBr. So here for the two representative methods utilizing the Horner-Wadsworth-Emmons reaction, we're seeing that the first reaction, we're having like EZ298 ratio. And then on the bottom part, we're having like EZ9 to 91% like ratio. And for the safety note and hazard warning, so first we have to read the chemical safety information. We have to identify the safety equipments and dress appropriately for the lab, since some of our reagents are corrosive and causes burn. So can we do this in lab? Maybe yes, maybe no, because again, some of the reagents used were expensive, and if we're gonna alter the reagents, it might give us like a different result and stuff like that. Also, the proper disposal of the chemicals. We have to know the properties of the reagents used. Also, careful manipulation is required before and during the distillation because bumping occurs so easily. This is particularly the case during the removal of solvent from the crude oil under reduced pressure. So for the discussion part, we do have methyl Z3 aryl 2 butanoates. So the synthesis is ubiquitous. E and Z, the unsaturated ester, is critical in organic synthesis because these important compounds serve as useful structural scaffolds for a variety of E and Z stereo-defined olefins. Although aryl or the Z2 have a simple structure, they are promising synthetic building blocks for a variety of stereo-defined alkenes. Despite their popularity, Z stereoselective synthetic methods are far more limited than those for E isomers, owing to the inherent stability of E cinnamate esters. Here, the authors or the people that worked in this reaction presented a simple, straightforward, and reliable synthesis of Z2 and its aryl analogs, including stereocomplementary E isomers. Also, this is the continuation of the discussion part. So the first is an 84% yield easy ratio to 98 ratio, that is like with the SNOTF2 and an ethyl bipyridine mediated reaction using the still HWE generis reagent number 3 with acetophenone that's developed by Sano and Nagao's group. That's the scheme 1 that was where SNOTF was like one of the reagents that are expensive. Also, there's another notable example developed by Kojima's group 4 is the reaction using 1-naphthoxy 2-PCH2CO2-ET HWE, which is this is the reagent that is not available commercially. But this reagent 4 with acetophenone using NaH to yield 80% yield, EZ9 to 91 ratio, despite the need for 48 hours at 0 degrees temperature. So the following are the relevant reported methods for the synthesis of Z2. The most straightforward method is to use Horner-Wadsworth-Emmons HWE reactions between acetophenone and the complex HWE reagents. So this the complexity of the reagents, I think that's what's making them like a little bit pricey and also not commercially available. And here, although these one-step methods yield high yields with good to excellent easy ratios, two of the reagents, 3 and SNOTF2, are expensive and reagent 4 is not commercially available. Also, other HWE conducted methods yield to moderate to low yield and or have low easy selectivity because of the use of specific phosphonate reagents. These approaches suffer from a lack of atom economy. Furthermore, the yield and easy selectivity of other aryl methyl ketone acceptors appear to be dependent on the nature of the ketones used. So like the yield and the product that we're gonna be collected, for example, if we're gonna perform this reaction, depending on like the nature of the ketones that we're gonna use, also depending on like what type of reagents we are using. So these are my references. I got the article from the Organic Syntheses website, and these are the authors. So we have Yuichiro Ashida. So he received his BS degree in 2012 and MS degree in 2014 from Kwansei Gakuin University. And we have Hidefumi Nakatsuji. He received a bachelor's degree in 2025 and his PhD degree in 2010 from Kwansei Gakuin University. Then we have Yutanabe. He receives his bachelor's degree at Tokyo in the laboratory of Professor Kenji Mori. He received his PhD at Tokyo Institute Technology. And we do have Yuji Suzuki. He was born in Tokyo, Japan. He received his bachelor's degree in 2016 at Tokyo Institute of Technology under the direction of Professor Keisuke Suzuki. And that's it for my presentation. Again, my name is Angelica Laine-Escano. Thank you.